Well, good morning, everybody. Welcome to the 2008 Director Seminar Series. I'm glad to have you all here. We are inaugurating the use of the new NAI Central Videocon room, which is a really nice facility, which Marco Bolt and Shige Abe had a lot to do with designing and operating, so I hope you'll all have a chance to see it. And we've got a great seminar series set up for this year. I'll tell you about some of the future seminars after today's talk. And right now I'd like to introduce today's speaker, who is Dave Hollenbach from our Ames Research Center team. Dave is an expert on the formation of protoplanetary disks and stellar formation, and the effects of protoplanetary disk processes on planetary formation. And he's going to be talking with us about that today. He has a bachelor's degree from Hope College, a PhD in theoretical physics from Cornell, and was a postdoc at Harvard before coming out here to Ames. He's been involved in a great many spacecraft missions, including KAO and SWAS and ISO and SERDIF. And in particular, he's a co-investigator on the SERDIF Legacy Program, Formation and Evolution of Planetary Systems. And today he's going to be talking with us about the effect of protoplanetary disk dispersion on planet formation. And I'll turn it over to Dave.
Thank you, Carl. So this is my first videocon, and this will be an interesting experience. And I'm very happy to talk a bit about the first question that astrobiologists ask, which is, what stars are going to have habitable planets? What types of stars? And what are the conditions that make it favorable for habitable planets to form around stars, and what places may there be unfavorable conditions? Now, you can approach this in an observational way or a theoretical way. I mean, observationally, Jeff Marcy and the planet hunters have been looking just to see which stars have planets and where they are. But we'd like to understand it theoretically of why planets form around certain stars. And that's sort of the kind of work that I'm going to be describing today. And as Carl mentioned, I'm part of the NASA Ames Astrobiology team with Dave Demery, the PI. So just to start off, since we're an interdisciplinary group, I thought I'd start off by talking a little bit about just the basics of planet formation that we astronomers now sort of have evolved this picture of planet formation. And I'll try not to use any jargon that the non-astronomer will not understand, but feel free to ask questions if I forget. I'm going to try to use this laser pointer. I hope you can all see this. There's a little red dot. To point to things so that if you're looking at my view graphs, you'll see them. So the picture is that in the galaxy, in the interstellar medium, there are clouds of molecules and dust particles. These dust particles are less than a micron in size, and they typically are silicate material or carbonaceous material. But mostly it's made up of hydrogen gas, these clouds, and they become fairly dense, and they form what we call molecular cloud cores, which are quite dense, and their sizes are in the order of 1/10 of a parsec, which astronomers use parsecs for distance. This is about on the order of a light year in size. And this material then gravitationally collapses. It has some angular momentum, and it spins. And so as it collapses, it forms not just a star, but it forms a disk. And in fact, it's the disk that probably feeds the material and makes the star grow as this collapse proceeds. The material kind of spirals in, hits the disk, and then accretes onto the star. This process takes maybe 100,000 years, a few 100,000 years. Now, an astronomical unit, which I have a typo here that should be big A, big U, capital A, capital U, and that will be in the future view graphs. You'll see that. That's an astronomical unit. One astronomical unit is the distance from the Sun to the Earth. And so 10 astronomical units is the distance out to Saturn, and 40 is the distance out to Pluto. So this gives you a sense of the scale of this disk around the star. Then in the disk, you initially have these small interstellar dust particles, and then the dust particles start to coagulate and settle to the midplane due to the gravity of the star, and there's a tendency to settle. They're orbiting in a Keplerian orbits around the star, but they settle to the midplane and they coagulate into bigger and bigger rocks and icy particles. And eventually these things coagulate to form planets in timescales of order of 10 million years. Now, The gas giants, like Jupiter, may take a little bit different timescales than planets like the Earth. I'll talk about that in the next slides. So let's just look a little bit at the formation of gas giant planets. There's two basic theories of the formation of gas giant planets. One is that they form by gravitational instability, and the other is by something called core accretion. And I'm going to focus in this talk just on the core accretion idea of the formation of gas giant planets. So in this scenario, as I say, you have a star with a disk around it. The dust particles settle to the midplane. There's some turbulence that sort of is pictured here by these little spirals. They accumulate into planetesimals, which are things that are maybe a kilometer in size, big enough that they can now gravitationally focus particles into them. They actually sort of suck material onto them. And then once that happens, you get a sort of a very rapid growth of these things that can grow up to lunar size or Mars size objects. And then there's a process where they collide, and you can eventually build up to sort of 10 to 15 Earth mass, what we call cores. And so it's just ice, rock, material, 15 Earth masses. Then its gravity is strong enough that it can actually attract a hydrogen gas, which is by far the most dominant mass component of the disk. And the gas can now be gravitationally attracted to this core, and it rapidly can build up things like Jupiter, gas-rich giants. Jupiter has something like 300 Earth masses of gas, but only 15 Earth masses of this sort of rocky, icy core to start with. And that may take a few million years. In fact, in the early models of this, it took 10 million years, and now we're beginning to realize that disks don't last that long. And so there's been a kind of a theoretical work that's being done to show that actually it can happen in maybe 3 million years or 2 million years. I mean, they're pushing it, but it does take some time for this all to happen. So that's how a gas giant forms, like Jupiter. The terrestrial planets sort of form in something that goes like step 1 and step 2 here, except that you build up these lunar mass objects, and at that point you only have sort of a few of them, and they tend to be on eccentric orbits which cross each other, and eventually they'll collide and merge to form larger and larger planets like the Earth. But that may take tens of millions of years, so that's a slower process, but it doesn't really involve the gas directly. It's just these rocks that get bigger and bigger and crash into each other, and it takes a somewhat longer time. So one thing that the gas does affect, though, in terrestrial planets is sort of how big they can grow and what kind of orbits they're on. If you have a lot of gas, I mean, if you have very little gas, then there's no gravitational interaction between the gas and these lunar-sized objects. And so they do collide. They have eccentric elliptical orbits that cross, and they collide, and they smash into each other. In fact, you know, it was one of the last collisions that's supposed to have formed the Earth-Moon system, where a sort of a Mars-sized object hit the Earth, and it ended up forming an Earth-Moon system. And in this case, you can build up fairly massive terrestrial planets. By massive, I mean as massive as the Earth, or maybe even a few times as massive as the Earth. And they tend to be on elliptical or eccentric orbits. On the other hand, if you have gas present for tens of millions of years that this takes, and you only need about 1/100th of a Jupiter mass, this MJ is a Jupiter mass, then the gravitational interaction between the planet and the gas, it's sort of a tidal effect, circularizes the orbit of these objects. And so then you tend to end up with many small sort of lunar mass planets that are orbiting, and you don't build up as large a planet. You sort of have a lot of moon-sized things that are orbiting. So the presence of gas in this for tens of millions of years, a small amount of gas, can make a big difference in forming terrestrial-sized planets. Now, as I say, one approach to this is just to look at things observationally, and this talk is going to talk about the theoretical underpinning of trying to explain these observations. But here's what we know in brief, observationally, is that the disks initially have masses that are about 1/10 of the mass of the star that they're orbiting. And if we look at very young stars, about 50 to 100% of them initially do have disks. So that apparently they collapse with enough angular momentum to form disks. This often happens. Now, if we look at stars that are older and older, as we look at stars that are 2 million years, 3 million, 4 or 5 million years old, what we see is that the dust in them disappears. This dust that initially is sort of small particles, and it's very opaque because you got a lot of surface area in these small particles, and so it's like a big opaque cloud. And they become optically thin, meaning you can see right through the disk in a few million years. The stellar photons can go right through the disk. And that only happens in a few million years. So something's happening to the dust very rapidly in the inner disk. And similarly, in the outer disk, we can measure actually the submillimeter radiation that this cold dust emits out there and see that it's diminishing in mass as well, at about the same time scale. So the dust is going away. And by that, I mean particles smaller than a millimeter. Now, it could be that one way that's going away is that it's forming planets. And if you form a planet, you become optically thin because even though the planet you can't see through, there's all this space between the planets that's just completely transparent. And the disk becomes thin. But there are other ways to get rid of the dust too, which I'll be describing. Now, there are some cases where we see a hole in the center that it's optically thin. You can see right through the inner part of the disk, but with an optically thick outer disk. One of the things that we're beginning to see just observationally with these radial velocity measurements of planets around stars is that this initial mass, which is a tenth of the solar mass or the stellar mass, doesn't all go into planets because you add up the mass of planets that we're detecting and they tend to be 10 to the minus 3 solar masses. That's true in our solar system as well. So most of this mass doesn't go into planets. It gets dispersed somehow. It either goes onto the star or it goes back out to space. Now, the radial velocity observations suggest that at least 10% of stars form planets. They've just done the statistics on the ones they've looked at. And, of course, they don't quite know how to extrapolate to systems that they can't see but might have planets, so it's at least 10%. So it could be that every star that has a disk forms some sort of planetary system. Or it could be that maybe of the stars that initially had disks, maybe 50% of them never formed planets or something like that, and the other 50, because the disk dispersed too rapidly or something. So we'll talk a little bit about things that compete with planet formation. Again, to give you a little more detail on how planets form, here is this early stage where the cloud is falling onto the disk, and one of the things theoretically we think may happen is that the disk builds up mass. Most of the material from the molecular cloud falls onto the disk, not directly onto the star. And the disk may build up mass until it gets to be about a tenth of the mass of the central star, and then it becomes gravitationally unstable. And this then leads to spiral waves and things that happen in the disk that allow angular momentum to be spread. And when that happens, material spirals onto the star from the outside in, and material starts accreting onto the star as rapidly as material falls onto the disk. Material is accreting onto the star. And it also causes a spreading of the disk. And in these early stages, the infall is so opaque that the effects of radiation from the star on the disk are nil because it's, the infall is keeping that radiation from the disk. If we now look at a later stage when the collapse has stopped, which is after perhaps a few 10 to the 5th years, and there's not much material flowing onto the disk from the cloud, then you get this situation, which is more likely the place where planets form. I should have mentioned that in that early stage, when you have this very vigorous accretion of material, any planets that could form that rapidly would probably be swept right into the central star. Whereas it's these later stages where the disk mass gets less than a tenth of the mass of the star, that the planets that form may survive and orbit, for billions of years. And in this stage, you still have accretion onto the star, but it's at a much lower rate, and it's driven by turbulent viscosity. And with this MRI is something that's a magnetic rotational instability, which is sometimes thought to drive this turbulence, which then leads to this spread of angular momentum. And that leads to accretion onto the disk of this, and so the disk mass then starts to drop from a tenth of the mass of the star to lower and lower values as material accretes onto the star. But at the same time, the reason the mass of the disk is dropping is that there are evaporation, or there are dispersal mechanisms that are going on. And there are several that are important. One is that the ultraviolet radiation and the X-rays from the central star shine on the surface of the disk, and they heat the surface up. And that drives photoevaporation of the outer parts of the disk. The disk gets thermally hot, the thermal pressure drives it out to interstellar space, and it evaporates. The other thing that can happen is that the wind from the central star can hit the surface of the disk and just entrain material and just drive it out to the interstellar space. And so material is entrained and driven out and lost from the disk. And I was talking about another one, which is a stellar encounters, in just a minute. But this whole process of planets forming, the material accreting onto the star, and dispersal mechanisms happening occurs over periods of millions of years. And there's a very intense competition going on between the planets trying to form, but there's dispersal happening simultaneously, trying to stop the planets from forming. So the effects of gas dispersal on the planet formation, and by gas dispersal, it's not only the gas, but the gas, when the gas is dispersed, it actually pulls with it the dust that is small. Everything less than a millimeter in size in dust particles kind of goes with the gas. But the bigger stuff can stay behind because the gas just passes over it. They're like cannonballs that don't get affected and still orbit the star. So the first thing that can happen is that it can affect the formation of gas giant planets, because if you get rid of the gas too quickly, there's no gas for those cores to attract, to form Jupiters. But secondly, the gas affects, as I've mentioned, the eccentricity and size of terrestrial planets, and it also affects planet migration. The planet pulls on the gas, and the gas pulls on the planet, and the net effect is a kind of a friction on the planets, and so that can cause them to actually spiral into the star, and they move around. It's called planet migration, and it affects the eccentricity of the planets as well, how elliptical their orbits are. In addition, it turns out that different mass stars are going to evaporate or disperse their disks in different time scales. And the more massive stars, for example, as I'll show you, disperse them very rapidly, and so there won't be time enough for planets to form around very high mass stars. And finally, because some of these dispersal mechanisms are getting rid of the material in the outer parts of the disk, where water and volatile-rich objects form, like comets, it may affect the formation of these things that may be reservoirs for volatiles and water-rich materials. So the outline of the talk is to look at these various dispersal mechanisms: the viscous evolution that makes things spiral out of the star, stellar encounters. We'll talk about stripping by winds and photoevaporation. I'm going to show you that viscous evolution and photoevaporation probably dominate these dispersal mechanisms. And then we'll put the two together, the two important ones, viscous evolution and photoevaporation, and see what the evolution of the disk will be with those two major ones going on. So the viscous spreading, as I mentioned, is this sort of friction because the inner gas is orbiting faster than the outer gas. And if there's any kind of friction, then the outer gas kind of rubs against the inner gas, makes it slow down, and then it spirals into the star. And you get this spiraling in to the star, where so the viscous accretion tends to spread the disk. This small amount of material gets more angular momentum and goes out, but most of it is being spiraling in onto the star. And when we do the calculations of this turbulent viscous evolution, we use a dimensionless parameter to sort of hide our uncertainties in processes called alpha. And astronomers talk about alpha disk evolution. Alpha then measures how much of this viscosity is present in the disk. And we kind of know what the value of alpha is just by observational constraints. We see how fast disks are accreting onto their stars, and we can kind of back up and see how viscous it had to be in order for it to viscously evolve. But we also have theoretical models of this magneto-rotational instability, which people have done very detailed numerical models of this evolution and found that alpha is of this order as well. And the way a viscous evolution works is that the time scales are much shorter in the inner parts of the disk. I've plotted time scales versus how far out in the disk you are, what radius out in the disk you are, in astronomical units. So one is the Earth distance. So this time scale is defined as follows. It's the surface density, sigma, of the disk at that radius divided by how rapidly that surface density is changing in time due to this spreading and this accretion inward. So when I say that if you have alpha of 10 to the minus 3 here at 1 AU, you find that the time scale is about 10 to the 5th years. Now that means, what that really means is that that material at 1 AU spirals into like a half of an AU in that time scale of 10 to the 5th years. That's the time scale to move a significant distance inward. But it doesn't mean that that material disappears at 1 AU in 10 to the 5th years. Because what happens if you viscously evolve disks is that most of the mass is contained further out in the disk at, say, 100 AU. And this material, where most of the mass is, replenishes the material that's inside of it. So as this material rapidly goes in, that's a small amount of mass there that rapidly goes in. You've got a lot of mass here, which the timescales are longer, but the mass flux inward is enough to replace it, because you've got a big mass, even though the timescales are longer, the m dot replaces it. So what happens is that the disks viscously do last longer than 10 to the 5th years at 1 AU because of the longer timescales for the material outward to go in. And it also means that what determines the lifetime of disks that are just viscously evolving is sort of the time scale out at the distance where most of the mass is, which might be at 100 AU. Well, I've kind of beaten that one to death. So let's look at, so I'm going to, by the way, you see this, you say, well, that's a nice graph, but I'm going to show other graphs of all these different mechanisms which will have time scales, and then we'll be able to compare them and see which ones are the most important. So sort of try to remember that one, but I'll show it to you again later. So here's the other thing about stars forming is that they tend to form in clusters. And so, in fact, we see some star clusters where there are 1,000 or 10,000 stars within a light year of each other. And that's, I mean, here at the sun right now, our nearest star is a few light years from us. So we're talking about much denser than the stars here. And so if we were born in that system, we would see a lot of bright stars out in the sky, very bright stars. And they tend to have these densities then they can have densities up to 10 to the 4th per cubic parsec, which is about per cubic light year, more or less. So you can calculate the close encounters that these stars will have with each other. And when they make a close encounter, the disk around one of the stars can get truncated. For example, I show this picture here. Here's a star going by a star and disk system. And what happens when you make an encounter is that you strip the material away to about 1/3 of the distance of the closest approach of that star. So if the disk is bigger than that, it will just be stripped down to that size of about 1/3 the closest approach by that encounter. So if you want to start stripping disks that are hundreds of AU, you need encounters that occur that close, of sort of 100 AU. So you can calculate the rate at which you have these collisions that come that close, which is 1 over the density of the stars times the velocity of the stars times this sort of cross-sectional area presented by the disk. And you find the timescales like this, which I'll plot. Here's the timescales. Now this is in one of the densest clusters that we know about, a very dense cluster like the trapezium cluster in Orion, where we have this sort of 10 to the 4th stars per cubic light year. And you see that if the disks are big, the timescales are very short because you do have a lot of collisions that occur within 1,000 AU of a disk. But if the disk gets small, the timescales get very long because you have to get really close encounters in order to strip those disks smaller and to make them lose their outer material. Now we'll move to another mechanism for dispersal, which is stripping by stellar winds, which historically was, if you asked people, well, what dispersed a solar nebula? People would have said it was the wind from the sun that eventually, just blew away the gas. Because we knew that not all the hydrogen went into Jupiter. We could tell from looking at the metal content of Jupiter that there was hydrogen missing. And so we said, well, that hydrogen just got blown away by the stellar wind. Well, that turns out probably not correct. We've done some more recent calculations of this stripping by stellar winds. The situation is that you have a disk like this, and you have a wind impacting it at a very glancing angle, and it impacts on the surface and it creates a shear layer on the surface, which material gets sort of entrained and driven out into interstellar space. And you can calculate the mass loss rate in the disk by basically taking the area and then multiplying by a flux. This is the density of the gas times its sound speed times an efficiency factor, sort of a flux of material from the disk going up into that mixing layer and then being carried out into interstellar space. And in doing such a calculation, our group has found that these are the timescales for around a 1 solar mass star with a typical wind that's about as strong as the early winds on the sun were, and with a surface density that looks something like what we think the surface density of the sun looked like as a function of radius. And we find that these timescales to get rid of the material at these different distances in the disk range from fairly short timescales in the inner part of the disk to fairly long timescales in the outer part of the disk. And we will compare these timescales with the other mechanisms in a minute. So now let's finally move to the final mechanism for dispersing these disks, and that's photoevaporation, which turns out to be the important one for the outer part of the disk. These are something that I've been working on for more than the last 10 years, and they're pretty difficult models to get right. It's a complicated process, so let's just run through a few of the elements that go into these computer codes. Our codes now take a week to run, and the fastest machines we have, a week to run one run of one particular disk at one instant of time. And of course, if we try to evolve it with time, it takes forever. And so we're really running into some serious computational problems. But so here's the situation. You've got the central star irradiating this disk. The disk's gas temperature does not necessarily equal a dust temperature. And I will show you some results from our code where we show that to be true. In the midplane, it is true that the gas temperature equals the dust temperature. But as you go up in the disk, the gas, because it has different heating and cooling mechanisms up high and can radiate to space, and dust radiates to space even more efficiently, the gas tends to get hotter than the dust up near the surface due to the heating by X-rays and UV. What we have to do is a self-consistent solution in the disk of its chemistry, because its chemistry determines its heating and cooling. So we got to do the chemistry, then we have to do the heating and cooling, we have to do the radiative transfer of how the photons escape from the disk, because they tend to be optically thick and they self-absorb and they eventually sort of percolate out. And then the vertical structure of the disk is determined by the gas temperature. So you have to self-consistently then, if the gas is hotter, it puffs up, and if it's cooler, it gets thinner. You have to do everything simultaneously and then do the dynamics of the flow. So we do make some approximations, and already it's fairly complicated. I want to tell you one or two things about the physics of this photoevaporation, just to get you sort of a better idea of what's going on. So regardless of whether you've got UV photons from an external star shining on the disk, here's a low-mass star like the Sun with a disk in this plane here, so we're seeing it edge on. You can either have external photons or you can have photons from the central star. You get the same structure. You get this inner part where this UV heating heats it up, and it causes it to puff more and more as you go out in radius, because gravity from the star is getting weaker, and so it puffs up more and more. The thermal pressure puffs it up. Eventually you get to the point where you have a flow out to the interstellar medium. And that point turns out to be roughly where the thermal speed of the atoms is equal to the escape speed from this system, the gravitational escape speed from the system. Now, EUV photons are those that ionize hydrogen, and FUV photons are those that are not energetic enough to ionize hydrogen. So it turns out that in terms of electron volts, it takes 13.6 electron volts to ionize hydrogen atom. So photons more energetic than that, which are about 912 angstroms, will ionize the disk, and these FUV photons will not ionize it, but they will heat it. Okay, so there is this characteristic distance where you get the flow. First there's a characteristic distance, let me say that, RG. That is defined as the place where the escape speed from the system, which is given by this formula, the mass of the star times gravitational constant over RG to the 1/2, is equal to the thermal speed of the gas atom, C. That defines RG. It turns out that if you actually do the details of the flow, that you do get significant evaporation even inside RG, down to about 2/10 of RG. So the critical distance where you get the flow is defined by RG, but it's more like 2/10 of RG. And so for EUV photons, which heat the surface gas up to 10,000 degrees by ionizing hydrogen atoms, that critical distance is a few astronomical units. But if you're at the FUV photons, they only heat up to 1,000 degrees, and so most of their mass loss is occurring beyond 30 AU. And there's another big difference is in that the EUV photons, because of the radiative transfer, tend to focus their evaporation right at this critical radius, so that they tend to try to burn a hole in the disk at 2 AU. But the FUV photons tend to evaporate from the outside of the disk in. So they evaporate the outside of the disk first, and then they sort of work their way in. Okay, so let's look first then at the photoevaporation by an external star. In other words, you have a low-mass star with a disk around it. Low mass meaning like the sun. Sun is considered a low-mass star. High-mass star is considered like 10 times the mass of the sun or 30 times the mass of the sun. And they're rarer, but they are incredibly luminous in ultraviolet, maybe 100,000 times as luminous as the sun, just in bolometric luminosity. Anyway, if stars form in clusters, the massive stars tend to be at the center of the cluster. You have all these low-mass stars that are sort of orbiting around the center of the cluster, maybe 100 or 10,000 of these low-mass stars. And they're at distances typically of 1/10 of a light year, pretty close. And this radiation from the star then heats up the surface, this massive star heats up the surface of the disk and causes it to photoevaporate. So here is a picture of a cluster. This is in Orion, and it maybe is a little washed out. I hope you can see it out there in television land. This is the Orion Nebula, so it's in the sort of sheath of Orion, sort of where its sword is. There's the trapezium stars, 4 very bright stars that form a trapezium. One of them, Theta 1c, is the brightest. It's about a 30 solar mass star. It's very luminous. And then you've got all these little dots are low mass stars that have formed in the last million years in this cluster of stars. And they're being illuminated by this very massive luminous star at close range. So here's a blown up picture of one of them. This is HST Tens, discovered by the Hubble. Well, actually it wasn't discovered, but the Hubble really took the great pictures of it. This is a Hubble Space Telescope image of this one star. The star, the low mass star, is not really seen in this picture. It's right at the center of this little green ring. And it's slightly obscured because the disk is sort of slightly edge on and you can't quite see the star. You can actually see it in some images. And then this is the disk, and it's sort of glowing in green. It's being heated up. The neutral gas is being heated up to thousands of degrees, and it's actually glowing in an atomic oxygen line that you see. Then there is neutral gas that's heated, that's photoevaporating off of this disk. And then by the time it gets out to where this bright region is, it becomes ionized due to these EUV photons that can ionize hydrogen that are being emitted by this very massive star, which is up in this direction, away from this very bright spot here. It's up this way. And so that those photons are then ionizing, and when this gas gets ionized, it starts to glow. And that's what's glowing, is this ionized gas. It's actually hydrogen. It's a line of hydrogen that's recombining, actually, but it forms this sort of reddish and bright glow. So this is actually, you're seeing a disk being photoevaporated here, and you're seeing the neutral material moving out and then eventually getting ionized by the ionizing photons from Theta 1c. So we've done theoretical calculations of how fast these disks will get evaporated by these external stars. So this is a plot that plots the mass of the central star, the massive star, on the horizontal axis, and then the mass loss rate on the vertical axis from the low mass star that's near this massive star. This is the mass loss rate. And over here, depending on the mass of the disk, this gives you an idea of what the time scale for the disk to evaporate is, from 10 to the 5th years to 10 to the 7 years. So the way you interpret this is that if you're a low mass star like the sun, and you're in a cluster of maybe 50 stars, and so your most massive star is maybe a 4 or 5 solar mass star, which is down here, then you will evaporate to 80 AU. You're evaporating from outside in this case, from an external star evaporating. You evaporate to 80 AU in a few million years. But if you're in a cluster of 2,000 stars, where your most massive star may be 20 or 30 solar masses, like in the Orion case, then you evaporate down to 20 AU or 10 AU in a million years. You evaporate to a very small radius. And then the viscosity will take care of that inner part very rapidly as well. So the whole disk will go away in short periods of time. So we can plot for the Orion conditions, which are fairly extreme, 0.2 parsecs from a 30 solar mass star. We can plot this time scale to evaporate due to the external star. So there's two E's, evaporation and external. And this time scale looks like this. The blue is by the evaporation caused by the hydrogen ionizing photons, and the green is the evaporation caused by the FUV photons, which can't ionize hydrogen. And this is as a function of the radius of the disk. So you see that there's very short time scales to evaporate the outer part of the disk. So the disks rapidly evaporate and truncate inward, and then eventually they get truncated to a point where viscous accretion takes over. So for astrobiology, the key question is then, what fraction of solar mass stars like the Sun spend a sufficient time close to a massive star in their early evolution that their disks are dispersed in less than a few million years, which is sort of the timescale we think we need in order to form planets, particularly gas giant planets, and thereby affecting the planet formation? And the answer, and Fred Adams has been working on this with Fatuso and others, and we've been working on this too, and we're trying to get it somewhat more accurately at the present time, but it's somewhere between 5 and 30%. So it's not a huge fraction of stars in our galaxy that this happens to. Maybe it's on the order of 10%, so that it is happening to some. And so there's going to be some systems where they were near a massive star and they just got their disk blown away, and it's really going to seriously affect planet formation, but it's probably not a huge effect. And we see that. I mean, as I said, Jeff Marcy and his crew has seen that there's a high percentage of stars that do seem to have planets. So this corresponds to what we're seeing. So finally, we need to look at the photoevaporation by the central star itself, not by some external star in a cluster. So this will happen to any star, even some isolated star that's born off not near a massive star. And so the same processes occur as that we've been talking about. So I'm going to show you a result from one of these models that takes a week to run. And I'm only going to show you the solution at 9 astronomical units from the star. So what we're looking here is at a vertical cut in the disk from the midplane, which is at 0 here on the horizontal axis, up vertically. Z is vertical height above the midplane. And then we're plotting both the temperature and the density of gas and dust. So this is actually the density of the gas here. Let's go with that first. So at the midplane, the density, which is shown over here, the log of the density is shown over here in particles per cubic centimeter. The density is 10 to the 12th hydrogens per cubic centimeter. It's quite dense. And at the midplane, you see that the temperature of the gas and the dust are both equal. And they're about, 70 degrees, or I can't read it, 50, 70 degrees. Then as you go up vertically, you see that the gas and dust, the density is dropping because you're kind of going up in the disk, getting up more in the atmosphere of the disk. The density is dropping rapidly, and the temperature then starts to rise because the gas and dust start to see the stellar photons, and that starts to warm them. At the midplane, they're just heated by the infrared radiation field of the dust, of the disk itself. But then as they get up higher, they start to see the stellar photons because they're up higher in the atmosphere where they can start to see the star. And they start to heat up. And the dust then, eventually, as it sees the stellar photons, reaches an equilibrium temperature of a couple hundred degrees. But the gas keeps getting hotter because it's being heated by X-rays and ultraviolet photons. And this is a situation of a gas of around a 1 solar mass star where we've put in some typical values of what the X-ray luminosity of these young solar mass stars are and the UV fluxes from these young stars. This shows AV of 1 is to the star. That's the AV in astronomers' lingo. Is kind of, this is where you start to get a real clear view of the star up in the disk, in the visible. And this is where the molecular hydrogen turns atomic because it's photodissociated by the UV photons from the star. This is where CO turns to ionized carbon because of the UV dissociation of CO and ionization of carbon by the UV from the star. You can see that eventually the EUV photons, which can ionize hydrogen, heat the gas up to 10,000 degrees here. In this case, at 9 AU, this is where the photoevaporative flow starts, right at the base of this ionized layer. This is where the flow starts coming off and you start evaporating the disk. Further out in the disk, it's this neutral heated gas by the FUV that actually where the flow starts. So that gives you an idea of these models and how they do the chemistry and the flow and the temperature of the gas. So if you do the central star, you get, this is for a 1 solar mass star again, the central star, this is the blue is caused by the UV photons that can ionize hydrogen, and the green is by the FUV photons. There is this tendency to burn a hole at 1 AU that the UV photons have. The timescales get short, your mass loss is high there. And then out here the FUV photons take over and they warm the gas enough to get a pretty vigorous flow going, and particularly short timescales at large radii. So that would tend to truncate these disks, and it makes disks very rapidly photoevaporate once they get bigger than 100 AU. So let's see how we're doing, okay? I'm now going to combine all these timescales to give you an idea of what now is the most important. And so we've got the viscous timescale in red here plotted as a function of the radius in the disk. These timescales to get rid of the gas. The wind timescales, the evaporation by the central star, by an external star, and by stellar encounters. First thing you see, stellar encounters are then rarely important. Maybe if the disks start off to be 1,000 AU in size, the stellar encounters will get to be important in truncating very big disks in these clusters. But what you see is the wind maybe has a little bit of importance at 10 AU, but it tends to be overshadowed by viscous evolution in the inner part. And it's certainly overshadowed by evaporation, photoevaporation in the outer parts, where these timescales get short. So this external star is a pretty extreme case, and even this extreme case doesn't compete that much with the central star's effect on the disk. So I'm going to ignore the external part, and we're just going to now plot the three important ones then that have the short timescales. You've got viscous accretion in the inner part, the winds maybe a little bit here, and then you've got the evaporation by the central star in the outer part. And as I said, this does not mean that the inner part goes in 10 to the 5th years due to viscous evolution. What happens is that this part of the disk lasts for a few million years out here at 10 to 30 AU, and then that viscously is replacing this material inwards that's accreting fairly rapidly onto the star. So that's the conclusion of these dispersal mechanisms, and you can start to see why disks lose a lot of their mass, and not all the mass goes into planets. So let's now combine the two important ones, the viscous evolution and photoevaporation, and see how a disk evolves. We're starting to do evolution calculations now. To do these, we've had to make severe approximations as to calculating the gas temperature. If we tried to fully do the chemistry and the thermal balance along with the evolution, it would take years on a computer. So we have this very simple, at this point, it's a very simple approximation, and we're working toward getting more sophisticated ones because it's very sensitive to the gas temperature. But I think this will give you an idea of what happens. I'm pretty sure that this gives a basic idea. So what I'm plotting here is the surface density of the disks. If you look vertically through the disks, how many grams per square centimeter is there in a disk, as a function of radius. And I'm showing you the evolution from 1 million years to 10 million years. We started off, I should have shown you the start-off point. It was a surface density that dropped as 1 over radius out to 200 AU and then was truncated at 200 AU, astronomical units. So what happens is that the viscous evolution tends to give you this 1 over r distribution of surface density. And because the mass goes as the surface density times the area, which is radius squared, most of the mass is actually out here at 100 AU, even though the surface density is higher inward. So what you see is that the surface density maintains a kind of a 1 over r squared distribution, and with just viscous evolution going on, the mass is dropping some. It maybe drops a factor of 10 in the disk because it's accreting onto the central star, but it also spreads. You can see this spreading effect. You're getting material now out of 1,000 AU or even 10,000 AU. It's just the disk is spreading. So we can follow that evolution even, so now let's add EUV photoevaporation. We just turn on the hydrogen ionizing photons from this one solar mass star shining on this disk. Well, for the first 10 million years, it's absolutely nothing happens. The EUV is too weak. Even this is a very generous amount of EUV for a one solar mass star early in its evolution. And even with this generous amount, it's identical to just viscously evolving for 10 million years. The EUV is trying to eat away at 1 AU, but there's just so much mass there, it's not doing much. So you have to wait for the surface density to drop at 1 AU for anything to happen. And so you have to wait for the viscous evolution to keep spreading the disk, accreting the disk, lowering the mass. So we now evolved it for 22 million years, and so the surface density now, this is at 10 million years now, the solid one. As you get close to 20 million years, the surface density drops enough that now the EUV, you see it eating at 1 AU. You see it eating this hole in the disk. And you can see this little kink right here as it starts to eat this hole at, I guess it's about 20 million years. And then in the next time step, which is just a little bit after that, it produces a gap at 1 AU. You can, we didn't quite catch it in this, so you can see a little bit of material still inside of 1AU, but very rapidly then the whole inner part viscously accretes onto the star. It just spirals into the star from 1AU inward, and you get a big hole in the center, and you get this torus of material outside of 1AU, which then the EUV photons eats from the inside out, and you can see this, here it is at one time step, at the next, it's eating it out, but viscously it's kind of, the disk has spread, so you have this torus of material out at 100 or 1,000 AU of dust and gas. So if this were really what was going on in planet formation, we would have, first of all, Uranus and Neptune, which don't have much gas, would be gas-rich like Jupiter and Saturn. If this is what were happening, we'd probably have more Kuiper Belt objects, more comets. I mean, might have more planets out at hundreds of AU. But we can observe that this is not what's happening. The dust and gas is not surviving this long out here at 100 AU. So it's not just viscous accretion and EUV photoevaporation that's occurring. So now we add FUV evaporation. This is without EUV. This is just the ones that can't ionize hydrogen, but they can heat up the surface gas, particularly out quite far. And you can see that what happens is that with a reasonable amount of this FUV luminosity, quite comparable to what we observe in these low-mass stars like the Sun, that with FUV and with the viscous evolution, what we have is that the outside is being eaten away by this evaporation. You can see that with time it's sort of truncating closer and closer in. The outside is being eaten by FUV. Viscous is trying to push it out, but as it pushes it out, it just gets evaporated away. And you can see that in a few million years, the surface density goes down. And very rapidly, you can also see that there isn't much left. I mean, once this combination of viscous evolution and photoevaporation are taking place, you don't have 10 to the minus 2 Jupiter masses to circularize the orbits of lunar mass things. I mean, it just goes away fast, very fast. All goes away. So now we combine EUV and FUV and viscous evolution, and that even shortens it a little bit more. Now it takes only about 2.7 million years for it to basically completely go away. And you can see that the combination of the FUV and the viscous evolution drives this surface density down, and then EUV burns a hole at 1 AU. You see this little gap. I should call it a gap first. There's a gap here, and then in a time step to 2.7 million years, all that material inside the gap, this material that's shown here, just all accretes onto the central star, and you get a torus that briefly exists between 10 and 100 AU, but briefly meaning 10 to the 5th years. This doesn't last long. That you have a little sort of a inner hole with an outer disk, but it isn't a long-lasting phenomenon. So it's maybe easier to see if I plot it just as the disk mass versus time. And so here I'm plotting the mass of the disk in solar masses, which starts off at 1/10 of a solar mass, around a 1 solar mass star. And this solid line, or this line here, is just viscous evolution. And you can see that the disk does keep getting less and less in mass as material accretes onto the star, but it's spreading and it's just lowering its mass to a factor of 10 over tens of millions of years. This we do not observe, and this would be an optically thick disk existing for very long periods of time, which we don't see. So that doesn't happen. If we turn on the EUV, it still lasts too long, but then the combination of viscous evolution and EUV does all of a sudden rapidly get rid of the rest of the mass. The EUV eats this hole in the disk, and then it rapidly photoevaporates the outside part of the disk, which viscously would have lasted a long time, but with EUV eating at it, lasts a short time. But then if you add the FUV from the star, the non-hydrogen ionizing photons, we get an evolution where the disk mass very rapidly cuts off to very low values at a few million years. And that's kind of what we see. And so we think that we're starting to theoretically understand what we see observationally, and we started to understand its effect then on planet formation and habitable planets. So very recently, over the weekend, we've been doing runs, and with this, and again, I warn you, kind of crude assumption about what the gas temperature is in these disks, because we can't do the detailed calculation. But we've done the evolution of the mass of the disk, like I just showed you the case for the 1 solar mass star, but we've done it around a 30 solar mass star and a 0.5 solar mass star. And you can see that in the 30 solar mass star, you start off with a bigger mass disk, because more massive stars tend to start off with a more massive disk. But because they have so much UV, they rapidly, in a few 10 to the 5th years, go away. And I think it's even going to be a little shorter than this. It's probably going to be more like 1 times 10 to the 5th years. but when we do the detailed calculation. But it's very rapid. So these, of course, these stars don't last very long, but the disks really don't last very long, and it's very unlikely places for planets to form. If you go to lower mass stars than the Sun, the interesting thing is first of all, they start off with a lower mass disk. Secondly, because their gravity holds the disks less strongly, we tend to get photoevaporation happening more rapidly, and so they more rapidly disappear too, and they start off with less mass. So if you are thinking that what planets need is to have a lot of gas and dust for the longest period of time in order for them to have time to form the planets, then it turns out that a solar mass star is a kind of a good place, because you can see that there's more mass in the disk and it lasts longer. To sort of integrate the amount of mass and how long it lasts, the one solar mass star is the best. And we think the cutoff where we really start getting rapid dispersion of the disk is probably around 5 solar masses. But we need detailed models of the temperature to really pinpoint that. So I'm going to conclude by summarizing and telling what I think are the astrobiological conclusions of this sort of theoretical description of how we think planets form and what kind of environments are going to be good and what kind of stellar masses are good for planet formation. So the summary is that photoevaporation is the dominant dispersal mechanism for the outer part of the disk, beyond a few astronomical units. Viscous spreading and accretion is what disperses the inner part of the disk. Winds and stellar encounters play little role in disk dispersal. The photoevaporation by the EUV from the central star, creates a gap at a few AU and then an inner hole, and then it rapidly photoevaporates the outer torus from the inside out. Whereas photoevaporation by FUV or by external star photoevaporates from the outside in, and it has a sharp outer edge and it just evaporates from the outside in. Now if you take this photoevaporation by the central star or by a nearby massive star, and what we find is that it evaporates the main mass reservoir of the disk. So this process, in conjunction with viscous evolution, determines their lifetime. It's not just viscous evolution that determines it. It's the combination of the photoevaporation and viscous that determines how these disks evolve in their gas and dust, and therefore how planets form. So I've tried to draw some astrobiology conclusions from this. I mean, there's some clear ones. First of all, there are stars born near massive stars that are going to just completely blow away their disks. The massive stars are going to evaporate these disks fast, and we probably see this happening in Orion. And so, but we think in estimating what fraction of solar-type stars that do this is probably on the order of 5 to 30%. So it's not a huge fraction, but there is going to be some disks that are going to be compromised and planet formation compromised. Stars more massive than about 5 solar masses don't need an external star to do damage. They're going to damage themselves. They're going to self-destruct. And they'll lose their disks in less than 1 million years and make it difficult for planets to form, particularly gas giant planets. And then the photoevaporation by the central star may lead to a peak in the disk mass and lifetime for disks around roughly 1 solar mass stars. That this may be the best place for habitable planets to form, because the disks have the most time to form the planets. And we've seen that in these models that we never have seen that we could keep 10 to the minus 2 Jupiter masses of gas lasting for tens of millions of years, which would then circularize the orbits of the Earth-sized planet, or of lunar-sized planets, and prevent them from forming Earth-sized planets. So I wanted to sort of finish on some caveats, though. Remember that for the disks that lose their mass in less than 3 million years, which is what I've been focusing on by this process of photoevaporation with viscous evolution, certainly giant planet formation is suppressed if it's caused by core accretion, which many of us think is the dominant way to make gas giants. So giant planets are likely to be suppressed. Now, they may have an effect on the likelihood of life. We know, because we know that, for example, in the Earth system, Jupiter has a protective effect. Dave Morrison is actually in the audience, and I can check with him, but I think it protects us from too high a bombardment by the Kuiper Belt objects and by objects that form comets. That the giant planets have a protective effect that way. We might get bombarded too rapidly if we didn't have Jupiter there. Now, okay, so these giant planets then may have some effect on the habitability of terrestrial planets, and what we're and of course if we're talking about moons around giant planets, then the giant planet will be suppressed in these cases. If we're talking about habitable life forming around moons. Now, less certain is the comets themselves, or the Kuiper Belt objects themselves that form comets that have all this ice and volatile, rich material. They may be suppressed because you see that we very rapidly get rid of this outer material. And so if we can get rid of the dust faster than it can coagulate into big enough sizes, and by big enough sizes I mean things that are centimeters or bigger in size. If it can happen faster than that, then it won't form these comets, these Kuiper Belt objects. Terrestrial planet formation, however, may not be suppressed, even in those cases where we disperse the disk in, say, 1 million years, because this coagulation at 1 AU of the dust particles to sizes big enough to form rocks is very rapid, we think. And so even if the gas got evaporated in a few times 10 to the 5th years, there may be rocks left which then can slowly build up terrestrial Earths. So we may have a class of system where there's a class of stars where they have terrestrial planets, but they don't have giant planets and possibly no Kuiper belts. It's impossible. So I'll leave you with that thought and conclude and ask for questions if there are questions.
Let's thank our speaker. Okay, if you have questions, please raise your hand on WebEx, and I'll take advantage of hosting over here to start off the questioning. Dave, if in general the gas doesn't last long enough to circularize orbits of terrestrial planets, how do you get circular orbits in a solar system like ours?
That's a very good question. Yeah, I have to say that it's a matter of degree, that the models that don't have gas in them and don't have anything else to circularize the orbits give elliptical orbits, but they're not that elliptical, but they are more elliptical than the Earth is. I mean, I'll say that. So there has been, when they do these models where the sort of the moons crash into each other and so forth, you end up with an Earth that's on a somewhat elliptical orbit. It's pretty circular, but it is elliptical, and it's more elliptical than the Earth is observed to orbit. So there's been this mechanism of the gas was an attempt to actually explain that. Was an attempt to say, well, what then did circularize the Earth to the almost exact circle that we're in? And it was an attempt. And I think that these models seem to indicate that probably won't work. And so we need something else. Another suggestion is that if when the Earth formed, there's a lot of small rocky objects around, they can have the same kind of effect. They can produce this sort of a dynamic, but you need a fairly high mass of these things. You need something that's comparable to the Earth mass in order to, or bigger than the Earth, somewhat bigger than the Earth mass in order to circularize the Earth. So maybe it's not gas, it's objects that are, rocks or moon, or smaller size things that circularize it.
Yeah, thank you. I see we have at least one hand raised on WebEx, so I'll turn it over to Marco.
Where do we have a question?
Thank you.
Okay. Fang?
Hi. Very nice talk. Great. I have a few questions that I'm not sure if I have the time to ask all of them, but let me ask two first. This is a probably technical point. So you said that when a gap is formed by the UV photon evaporation of the inside of the disk, then mass will flow inside from some perhaps the most massive location. But does the same thing happen when the FUV photons evaporate the outside part of the disk? That mass will flow outward. Does that occur?
Yes, it does.
Is that a significant effect?
What happens in the cases that I showed with a combination of, say, the FUV photons, which are heating the outer part of the disk, and viscous evolution, what's going on is a competition between the viscous accretion is trying to spread the disk out further, but then evaporation is trying to truncate it. And so you sort of reach a kind of a quasi-steady state distribution of surface density such that the viscous evolution is pushing things out, and then the photoevaporation is driving things in. And so the solutions you saw sort of reflect that tension between the two processes.
Great, thank you.
And then the
Second,
inner part where the gap is, yeah, it's just that once the gap forms due to the EUV photons, then the inside no longer is getting, the outside can't accrete to replace the inside because there's this gap. And because everything that comes in is being evaporated by the EUV photons at that gap. And so nothing is replenishing the inside. So when the inside doesn't have an outside source to replenish it, it very rapidly just accretes onto the central star.
great. And in one of your slides, I think it's very new results continue, probably has a 6. Basically, what I want to ask is, in all those figures, UV, FUV, those are only considering the contribution from the central star, not the external star. Is that correct?
Yes. I think, I don't know if you can see my view graphs, but yeah, all the very new results, yeah, because what happened historically was that I worked on the external stars first, and so the newer results are the internal stars. In some sense, the external stars are a simpler case because the radius, well, it's just, the problem with the central star is that the disk flares in response to this heating of the surface, and then the rate of transfer to calculating the heating depends on all your solutions on the inside and how the photons from the central star can make it through the inner part of the disk out to the outer part of the disk. And so it's more complicated. When you have an external star, basically what the most of the photons are evaporating the outside rim of the star first and then working their way inward, and there isn't this complicated treatment of the rate of transfer of the photons going in. Yeah, so all these were just from the central star at the end here, yeah.
Do you always assume that the disk mass is 10% of the star mass?
No, we can vary that. The reason that I chose that was that based on the sort of theoretical idea that in the initial formation of the disk mass builds up until it becomes gravitationally unstable. So it's hard to get it more massive than 0.1 of the stellar mass, because then it really gets violently gravitationally unstable, and it starts to really rapidly either form a binary or accrete onto the central star. And actually the first thing that happens is it starts to really accrete rapidly onto the central star. So that's the starting point, is based on that idea. That's the threshold just where you start to get gravitationally unstable. And it's roughly 0.1 solar masses. It can be a little more or less. But we can, in our models, of course, we can start with any mass we want. If we start with lower masses, then we get shorter timescales.
Okay.
Dave, let me ask a different sort of question. We often hear of planetary rings being proposed as analogs for protoplanetary disks, in particular Saturn's rings. And of course, there's been a lot of study from the Cassini mission in particular of gravity waves, etc., and other features in Saturn's rings. To what degree are planetary rings, and Saturn's rings in particular, a good analog for protoplanetary disks, and to what degree would we expect to see the same kind of physical phenomena in a protoplanetary disk that we see in Saturn's rings?
Good question. Well, of course, a big difference compared with these models is that if you have the rings around Saturn, the thing that's going to photoevaporate them will probably be the sun. And so then the question is, at what point does the stellar photons make it to Saturn's rings? I mean, if Saturn formed and the rings are starting to form in a situation where you still have a gas disk presence and dust disk, then the stellar photons won't make it in. They're sort of analogous in the sense that it's true that in these rings there's the same processes of coagulation of particles, sort of settling to the midplane and the coagulation of particles. So that part of it is similar in Saturn's rings. Yeah, I mean, Saturn's rings in the planet system, there's been time enough so that there's been a kind of a sweeping out. There's a growth of these particles to the point where they actually get gravitationally important and they start to sort of focus other particles in. In Saturn's rings, everything is small still, and so there isn't any of this, and there isn't a sweeping up so that you just end up with a few things. It's a good question. I haven't really thought about it that much, but it's certainly possible that in the formation of the rings around the planets that photoevaporation by the sun may have played a role in affecting the evolution of these rings. If they if they did get exposed to the solar radiation.
Thanks.
We have a question from the Ames team.
Okay.
And then from David.
Hi, Dave. This is Dave DeMarais. I wonder if you could make some comment about volatiles in the context of this. And I'm thinking about that poor Oort cloud out there, which that sounds like a pretty brutal place to be based on your evaporation models. And then also just what the impact of your models have on the delivery of volatiles to the Earth. I mean, it seems like many people think that this is a later stage kind of thing, and it sounds pretty brutal in the later stages of your model. So I was just wondering if you could comment about where volatiles end up.
Okay. Well, the Oort cloud, is supposed to originate actually from material that formed probably, around Neptune, and so it's true that the Oort cloud's way out there now, and that seems like a very brutal place in terms of this photoevaporation model, where things on the outside happen very rapidly. But I think the Oort cloud is the sort of ejecta material that formed in closer at say tens of AU, and so the question is then, you're forming these things that are probably kilometers in size or bigger, or hundreds. It could be up to 100 kilometers in size, but things of that size. And if you can just form if at tens of AUs you can form those icy rocks big enough so that they'll withstand this evaporation, then they can eventually coagulate into objects that form comets. So the question really is can you evaporate faster than the material can coagulate into bodies that are big enough to withstand the evaporation? And that I'm not so sure of, because this timescales for coagulation of these particles building up to sort of centimeters or meters in size is not so clearly understood yet. Coagulation is sort of a dicey topic. So it's possible. That's why I'm a little waffling on this. When I mentioned these Kuiper belts, that they may be suppressed, but I'm not sure. It just depends on how long the coagulation process takes to get them big enough to withstand things at tens of AU. Because the photoevaporation is going to remove all the small icy bodies and less than a millimeter in size, and the gas, and as you see, in timescales can be timescales of less than 1 million years. And the coagulation timescales in the solar nebula get bigger, longer as you go out. And so there is a point where the coagulation timescale, just even to build up a millimeter-sized particle, gets to be pretty long. And at that point, you will just truncate the ability to form any kind of ice. Now, I know that there's been a lot of work done on what's delivering the volatiles to the Earth. And one, I think the lead author was Morbidelli, but talked about the reservoir maybe from the asteroid belt, with some sort of water-rich objects in the asteroid belt, which is sort of inside of Jupiter. And those regions, again, are fairly close in, and they're subject to this. I mean, in these models where you have the photoevaporation combining with viscous evolution, eventually the viscous evolution does get rid of that inner part of the gas in the dust. But that does typically takes millions of years, and presumably there would be time to form some of those objects. So I think that in terms of just to summarize, my guess is that in the extreme cases where you evaporate, the whole disks are evaporated in like less than 1 million years, and maybe even less than 10 to the 5th years, like an extreme case of a disk around a very high massive star or a low mass star very close to a high mass star, then you may affect the volatiles. But in a case where the disks take, like in the sun's case, the disk takes millions of years to evaporate, then I don't think there is much of an effect.
Dave?
Dave, that's interesting and over my head in many ways, but I'm going to try to give you a hard time in any case. Because of the element that after the disk is largely dissipated, I had the impression you were talking about the planetesimals kind of automatically coming together. And surely that depends on whether or not there is a giant planet like Jupiter. Just as today the stability of objects in the asteroid belt depends on Jupiter. And I'm just curious about that role. Surely you cannot completely decouple the presence of external giant planets from what's happening in the terrestrial realm inside.
Right. And that's a really good point, and that's one that I would like to understand further, because I think that what my work, or the work of my group, is showing is that the gas giants, if they form by core accretion, can really be affected by these processes. And I think that it's even happened here in probably the solar system, that the evaporation by the sun, the early sun, probably got rid of the gas, which is why Uranus and Neptune don't have much gas, and why we don't have that much material outside. I think it's already has had an effect on the planet formation. But you're certainly right that the giant planets not only serve, I was sort of mentioning this idea of protecting us from comets or something, but they also serve to sort of stir things up and therefore affect the collision rates of things and so forth. And that's not something that I've really looked into. But I think it's a good point that it would be good for us to understand, all the different effects that giant planets have on the habitability of, say, terrestrial planets in the system.
My guess is that for all of the fact that Jupiter now protects us from comets coming in, most of the comets that are coming in were placed there originally gravitationally by the giant planets. So, it's just protecting against the problem it caused in the first place.
But what if there hadn't been a Jupiter, you would have formed all these icy comets, and wouldn't they still be coming in? You may not have an Oort cloud. Maybe it was the giant planets that threw them out there, but you'd have a Kuiper belt, right? And so it seems like you might have a very rich Kuiper belt. I don't know if you didn't have photoevaporation. And so then maybe you'd have some really heavy bombardment. I don't know.
Maybe they will not be disturbed as much as they were in the solar system in that case.
Yeah. But I think, no, that's true. That's true. I guess the Kuiper belt objects, the short period comet objects, they are disturbed by the large planets. In terms of it's not like their self-interaction. Yeah.
Do we have any other questions? Any hands raised, Marco? Bang.
Hey, how about the magnetic field of the star? Is that significant or not?
Well, it's significant in our. As I said, we have buried all our ignorance in this alpha parameter, which is that just describes how the disk viscously evolves. It's a dimensionless parameter, and observationally, by looking at how fast the disks are accreting onto the star, which we can measure, because as they accrete onto the star, we see an extra luminosity in the ultraviolet. We see spectral lines that can give us an estimate of the mass accretion rate on the star. So by looking at those mass accretion rates, we get an idea of what alpha is. Now, we don't have any theoretical understanding of why alpha is that value. But one idea is this magneto-rotational instability. Now, that involves the magnetic field of the star, which then threads through the disk, and then the disk is sort of is Keplerian orbiting, and you get a kind of a spreading of the magnetic field in the plane of the disk, and you get instabilities in it. And of course, as the magnetic field moves around and gets unstable, it drives the charged particles with it, and the charged particles then drag the neutral particles, and you get all this turbulence happening in the disk. And that's the idea. That because those kinds of models have been giving alphas of order the ones that are observed. And it's one of the few that seems to work reasonably well. People have looked at other possibilities, and the MRI is the favored one now. The only thing about this particular instability is that it requires there to be a certain amount of ionization in the disk, because the magnetic field moves the ions, and then the ions have to collide with the neutrals to get the neutrals, which is most of the disk, moving. And so in this, there's these dead zones in the disk where there's not enough ionization for the ions to actually move the neutrals. There can be these dead zones, and of course they may be favorable then to planet formation because they're not as viscously evolving. They're just sort of sitting there waiting for gravity to bring things together.
Well, regardless of the accretion source, is the presence of a magnetic field sufficient to keep some of the disk gas around after the FUV, say, has liberated it from the disk? Like for example, think about there's the. I don't want to get too far into astronomy, but there is the the X-wind scenario where there are lines threading through the disk, and also there's a whole remnant on the large scale is interested in that proplet, like way beyond the disk. There is this FUV that is ablating away the cloud, but the cloud itself has a remnant magnetic field. How much does the fossil field from the cloud, in addition to the star's field, help entrain this? obviously at some point the FUV wins, but is there like, you know, some significant effect that helps these help the gas stick around?
I can't think of any, to be honest. I mean, in the first place, if there are magnetic field lines threading it in some way, I mean, the material can always flow along the lines because there's no force along the lines, only perpendicular to the lines. And so, you know, the material, this thermal evaporation is just one that's driven by thermal pressure, and it'll just move along whatever, if there is some sort of external field that is actually controlling the motion. I mean, the magnetic fields are pretty weak. I mean, in most of our models, I mean, it's true that right near the X wind, which is the origin of these protostellar winds, which is just a few stellar radii away in the disk, those fields tend to be like a kilogauss, or they're quite high, or maybe less, but they're quite high. But as you get out, it seems that the magnetic fields are getting weaker and weaker, and the thermal pressures tend to be quite strong. I have a feeling that thermal pressures will pretty much dominate the flow.
Okay, well, let's thank our speaker again. And I would just like to let you all know that the next two seminars will be given by Bill Schopf on February 25th and by Jody Deming and Jim Staley of the University of Washington on March 31st. Bill, on February 25th, is going to be talking about his work on looking at microfossils using confocal laser spectroscopy and Raman microscopy as well. And Jody and Jim are going to be talking about cycrophiles and particularly those organisms as models for potential life on Europa and Mars. So I hope we will see all of you there and others. And thanks once again to Dave, and see you all again in a little while.